In the last session, we have seen how to determine the inverse kinematics of SCARA manipulator. In this session, we will see how to determine the inverse kinematics of Stanford manipulator. So it is a 6 DOF manipulator. So here, so the transformation matrix T, it is the known transformation matrix, that is which represents the position and orientation of the end effector plate. So this is the forward kinematic model of the manipulator. So the Stanford manipulator, this is the forward kinematic model. So now we will be, so this is according to the previous, so this is AX, AY, AZ, right? So we'll be equating this term to AX, which is the known value in your transformation in the given end effector post matrix, and this is dx, dy, dz. So just by equating this transformation matrix with the known transformation matrix which corresponds to the elements ax, ay, az and dx, dy, dz, we will be getting 6 equations. Okay, so those 6 equations are stated here. So that is C1, C2, C4, S5 minus, so this is here, that is 1 cross 3 term, so that is equated to AX, then DX, AY, DY, AZ, DZ. So you get 6 equations. So now in this equation, you can see that this term, right? So this term and this is one and the same, right? So just substituting it in this, you will be getting L6AX. Okay, L6AX plus C1S2D3 minus S1L2 equal to DX. Right? The same way, this is this term, that is S1, C2, C4, S5. This term is same as this. So just substituting this in here, you will be getting L6AY plus S1, S2, D3 plus C1, L2 equal to dy, right? So here rearranging this eighth equation, we will be getting C1, S2, D3 minus S1, L2 equal to dx minus L6 AY. And in the same way, after substituting the 4 into 5, you will be getting an equation, and also rearranging that, we will be getting S1, S2, D3 plus C1, L2 equal to dy minus L6 AY. Now, as we did for SCARA, again we will be just using these 2 equations. We will be squaring and adding on both sides and applying the trigonometric identity. You will be finally getting the expression like this. So the 10th equation, you have got it by just squaring and adding equation 8 and 9, right? And also the remaining 2 equations, that is the 6th and 7th equation, when you just combine and rearrange and squaring, you will be getting, so rearranging, you will be getting C2D3 equal to dz minus L6AZ. So on squaring both sides, you will be getting C2 squared D3 squared is equal to dz minus L6AZ squared. So from this 2 equations, you can just solve for D3. So you will be getting D3 is as given in equation 13. And you know D3 is always positive, as because it represents the prismatic joint variable. D3 is always positive, and so there is no possibility for considering taking the negative solution in this square root to be valid. So only the positive value of it we will be taking. So D3 is equal to the positive square root value of the given equation given in equation 14. Okay. Now we will solve for D3, and we will just try to solve theta 2. Right. So from the equation 10, we will be getting S2 D3 is equal to plus or minus root of dx minus L6AX the whole square plus dy minus L6AY the whole square minus L2 square. Dividing this equation by equation 11, you can get the, as because it was C2 D3 in equation, you can solve, D3 is now known to you, right? So you can get the solution for theta 2, right? So the theta 2 will be in form of A tan 2, right? So this is 60, equation 60. It gives you the value for theta 2. So now we have got D3 and also we have got theta 2. Now let us try to get the value for theta 1. So for this we will be again using the same procedure on how we derived when used in SCARA. That is, you will be using the trigonometry identity by taking k1 is equal to r sin alpha and k2 equal to r cos alpha, where r is equal to k1 root of k1 square plus k2 square, and pi is a tan 2 k1 by r and k2 by r. By just using this trigonometric substitutions, we will get these two equations when we just apply in equation 8 and equation 9, right? So just substituting that, you'll be getting sine. So this same procedure we have already done in SCARA, right? So I think it would be easy to follow here. So we'll be getting it in sine pi minus theta 1 and cos pi minus theta 1. So from that, we'll be getting theta 1 easily by, because pi is already known to you. Pi is known to you, right? So pi is known to you. So from that you can easily get your theta 1 value by taking by dividing equation 21 and 22. You will be getting it in the tan 2 form. That is pi minus theta 1 is this. So you have substituting for the values. So you will be getting the theta 1 equation here, right? So now what we have got? We have got theta 1, theta 2, and also d3 we have got. So Stanford manipulator is a 6DO of manipulator. So we need to get the remaining joint variables, that is theta 4, theta 5, and theta 6. So for this we will be using another approach. Okay, so we'll see what it is. So here you know the complete transformation matrix T6 to 0. It is the product of the six transformation matrices from, that is T1 to T2 to 1, T3 to 2, T4 to 3, T5 to 4, and T6 to 5. Right. So this it is represented graphically as here. So, right. So you have the transformation matrices which is represented here, and the product of that will be giving you T6 to 0, right? So here you can see you have two paths, right? Starting from this frame 3, you have two paths. That is, either you can just go from frame 3, 4, 5, 6, or you can just go from 3 to 1 0 to reach the overall transformation matrix. So along this path, that is T 3 to 6, this can be obtained as that is this transformation is complete path. So which denotes T 3 to 6. This can be obtained as just multiplying the three transformation matrices as shown here, right? That is T4 to 3, T5 to 4, and T6 to 5. So when we just multiply the transformation matrices, you'll be getting T6 to 3, right? So when you just consider another path, that is the path 2 from frame 3 to 1 to 0 to reach frame the 6. So in this path, if you just supposing if this is the path, then that is the path from via the base, then the tool frame, it is defined with respect to the base, and hence it can be reached from frame 3, which is by traversing to the links of the arms. It can be reached from the frame 3. So we can write that as T 6 to 3 is equal to T 2 to 3, 1 to 0, 0 to 1, and 6 to 0. So by multiplying these four transformations, you'll be getting T6 to 3, right? So we know that Ti to I minus 1 is equal to Ti minus 2 I the inverse. Okay, so and T6 to 0 is simply the transformation matrix 3. So you are just applying it here. T6 to 3 is nothing but the inverse of T3 to 2, and that is the inverse of this matrix, the inverse of this matrix, right? That is T2 to 1 inverse, or I'll just write it separately here. That is, we are writing that matrix T2 to 3 is equal to T3 to 2 inverse. Okay. Likewise, T1 to 2 equal to 2 to 1 inverse, right? So next t 0 to 1 will be equal to t1 to 0 inverse, and t6 is written as t, right? So the transformation matrix, so this equation we are just rewriting with its inverse components in this equation, right? So why do you want to do that? Because we know this theta 1, theta 2 and d3. So all the three joint variables we have found. So the matrices, this that is this three matrices can be and their inverse can be easily computed. So just substituting the values and multiplying these matrices, you will be getting this T3 to T6 to 3 matrix you will be getting, right? Because all the values in the right hand side it is known, and we have to just substitute those values and we will be getting this. So let us say that you have just got your T6 to 3s this. Now this is the known values. All the values here are known values. Okay, so you can, let us denote it as the values, that is R11, R12, R13, etc. Right? Now from this you will be just using that, you will be now equating the components of the transformation T matrix in order to find the remaining joint variables. So so from the in the matrices, the equation 25 and 27, they will be representing the same points, the arm point, the theta 4, theta 5 and theta 6, they can be found just by equating the corresponding elements of the matrices. So first for theta 5, the element in the third row, they are just equated so that you will be getting. So by equating each component in the third row, that is R31, R32, R33, you will be getting this, right? So in order to get theta 5 and theta 6, we are just solving this. So just squaring and adding these two equations. So 28 and 29, just squaring and adding, and then dividing the result by this cos theta 5 equation, you will be getting the theta 5. Okay, so this is the equation that you will be getting for theta 5 after squaring and adding these two equations and then dividing it by this equation. Okay, so then after equating the elements, that is 2 comma 4 and 1 comma 4, you can get these two expressions, that is minus L6 S4 S5 is equal to R24 and minus L6 S4 S5 is equal to R14, and from these two equations you can solve for theta 4. Okay, from these two equations you can solve for theta 4, as because you know theta 5 is now known. So if you just use these equations, you can solve for theta 4. So you will be getting the theta 4 expression as A tan 2 R24 by S5 and R14 by S5. So all are known. So here S5 is known, as because theta 5 is known, S5 is also, the sine theta 5 is also known, and R24 and R14 are already known. So from that you can just get theta 4. Now, all the variables we have got, that is theta 4, theta 5 is also known. The only unknown here to get it is theta 5. So, using the equation 29 and dividing that equation by equation 28, you will be getting the theta 6 value, right? So, this is the expression for determining theta 6. So, all the joint variables, that is theta 1, theta 2, d3, then theta 4, theta 5, theta 6 of the 60 UF Stanford manipulator has been derived for the given end effector force.